Very good morning. We are discussing on tutorial of ANOVA and the supplement. It is under the supplement and it is continued. So today we finish 2-way ANOVA tutorial and then we will also discuss 3-way ANOVA. I am sure after this class, considering all the previous lectures on ANOVA, you are definitely going to have that confidence that what is analysis of variance and how it is can be used and the findings can be interpreted in real life situations. Let us see the next.
We will consider tutorial on ANOVA. So, last class what you have seen that we consider two tutorials, one way ANOVA, another one 2-way ANOVA, and we have added now one more tutorial on 3-way ANOVA. We have fully completed 1-way ANOVA, partially completed 2-way ANOVA, and we have not completed 3-way ANOVA. So, now I will complete first the 2-way ANOVA and then we will go for 3-way ANOVA. Let us come to the problem for 2-way ANOVA. As I told you that the issue is safety behavior of a company across different departments and different age groups. We have considered 3 departments A1, A2, A3 and 3 age groups less than 30 years of age, 30 to 45 years of age and greater than 45 years of age. This table shows the different data points collected across departments and groups. For example, in the first cell 68, 65 and 70 data values, these data points are obtained for the combination A1 and B1. Similarly, for A1 B2, A1 B3 like A2 B1 and finally A3 B3. So, there are 3 samples. So, in the sense that the size of the sample for each combination is 3 and totality, in total there are 27 observations and across each department there are 9 observations, across each age group there are 9 observations. And our objectives are, do the different departments differ in their safety behavior, do the people in different age group differ in their safety behavior, and are there relationship between departments and age groups. So, we have discussed this and we have seen this table and also we have discussed that what are the different way the computational formulas for computation of SST and its subcategories from sources of variation point of view. So, I think all of you know at this point in time that our total sum square total is divided into sum square factor A, sum square factor B, then sum square factor AB means interaction AB plus sum square error. So, we have divided in this manner and we have also seen that the degree of freedom is n minus 1 for total sum square. For SSA it is L minus 1, for SSB it is our m minus 1, for SSAB it is L minus 1 m minus 1 and for SSE this is Lm into n minus 1. So, that we have already seen. So, ultimately for the example given there are total I think 27 observations minus 1. So, that is 26, this equal to there are 3 departments. So, 3 minus 1 equal to 2 plus 3 age groups, that also 2 plus 2 cross 2, that is 4 and rest will be this L is 3 into 3 into 2, that is 18. So, if you add this 2 plus 2 plus 4 plus 18, that will lead to 26. Okay. And also you have used the formula, computational formula for SST and SSB, SSA, all those things using this formulation, that first you compute the grand mean, then individual factors level mean, factor B levels mean, and the combination, these are all totals. So, first grand total, then factor A level totals, B level totals, and AB, that interaction total. Then following this equation you are getting SST, SSA, SSB, SS subtotal, then finally you are getting SSAB using this equation, and this is the formulation final SSE. And then what we have done, we have also seen that the ANOVA table. This is the ANOVA table, sources of variation, different values, then degrees of freedom, and you found out that 87.82, this is the MS for factor A, for factor B it is 139.82, for factor the interaction A and B, that is 55.09, and SSE 19.48, and then the F statistic values are for factor A 4.51, factor B 7.18, factor A interaction AB, that is 2.83, and these are the probability values which we got from the F table. Now, what is the degrees of freedom for this? For this, degrees of freedom is, numerator degrees of freedom is 2 and denominator degrees of freedom is 18. For the second one also, numerator degrees of freedom 2, denominator degrees of freedom 18, and for AB, numerator degrees of freedom is 4 and denominator degrees of freedom 18. Okay. So, all cases this F, then we found out F some value you got, suppose this one is this, suppose F 2 18, if this is 4.51, then this probability value is, this one is 0.026, this is the meaning. So, two ways you can do it, one is you fix one alpha value and then find out that what will be the F value for that alpha. Suppose if you take F 2 18 0.05, you will get certain value, definitely that value will be less than this value, that is 4.51. So, the first factor contribution is there and which is much lower than 0.05 significant level, second factor also same, but third factor which is the interaction factor, it has it is slightly more than the requirement, that is 0.05, that is 5% probability level, but it can consider it significant. Okay. So, there are differences across age groups, there are differences across departments, and interaction is significant at 5.6% probability level. Then I told you, we also discussed this, that I told you that how do you estimate the parameters. These parameters are written clearly here, these are the parameters. So, I am writing once more that XILM equal to mu plus mu L minus mu plus mu M minus mu plus mu LM minus mu L minus mu M plus mu, then plus XILM minus mu LM, and which, so that what does it signify then? This is nothing but the grand mean, this one is tau L, then this one will be beta M. So, grand mean tau L beta M, and then tau beta LM, this one plus epsilon IL, and their sample, this is population, from population. So, their sample counterpart. So, if we find out XILM, it will be, we have written like this, G bar, that is the grand mean bar, plus we say AL bar minus G bar, grand mean bar, plus we say BM bar minus G bar, plus we say that AB LM bar minus AL bar minus BL bar, BM bar, not BL, AL BM bar minus AL bar minus BM bar plus G bar plus XILM minus ABLM bar. So, this is in the sample domain. So, that means the estimate of mu is G bar, estimate of tau L is we say AL bar minus G bar, estimate of beta M is again BM bar minus G bar, then estimate of tau beta LM, that total cap, this one is your AB bar that LM, or we can give a bracket here, okay, AB bar LM minus AL bar minus BM bar plus G bar, and your error portion ILM cap, which is XILM minus AB, again you make a bracket here, AB bar LM. So, this is this parameter, estimates of parameter, different parameters. And now you see then what will be your that predicted value of XILM, ILM. So, everything will remain except the error term. So, this one. So, this will be G bar plus AL bar minus G bar plus BM bar minus G bar plus AB bar LM minus AL bar minus BM bar plus G bar. So, what will happen here, you see this few things will be cancelled out, G bar will cancel out. Okay. Now, one more G bar is there, G bar and this G bar will be cancelled out, AL bar plus AL bar minus will cancel out, BM bar plus BM bar minus will cancel out. So, ultimately what will remain then, this is nothing but AB bar LM. This is the predicted value, correct. So, if I go back now, so what will be the predicted value for each of the cell, what is the average in this cell, that will be predicted value for first 3 quantities. In the second cell, the average of this will be the predicted value for all 3, third cell like this. So, every 3 observations having the same predicted value. Okay. So, now let us see this final one, what we have, this is what is all the values computed. So, AL bar, I said we will calculate something more with this A1 bar. So, A1 bar equal to 71.56, this is computed. Now, A2 bar is 77.22 and A3 bar is 71.89. What is our G bar? G bar is 73.56. G bar is this. Suppose you want to find out that you are interested to find out tau L bar, then what you will do? This minus your thing will be 71.56 minus 73.56. What will be the value? This will be minus 2. So, what does it mean? That the A1 effect, department 1 effect is minus 2, that is with respect to the average we are talking about. Then second one will be 77.22 minus 73.56. What will be the value here? 77.22, 73.56, 6, again 6. So, this will be 4. So, 3.66. And third one will be 71.89 minus 73.56. So, 71.89, 73.56. So, 3, then another 3, then this will be what? I think just opposite. This is smaller, 71.89, then 7, this will be 8, 9, 9 plus 6, 15, 2, 1 minus 1.67. Now, you add this is 0, this 6 and 7 there is some rounding error, otherwise this quantity will be 0, and I think you can remember that I say that tau L equal to 1 to capital L, this will become 0. So, the same thing will prevail for beta. So, what will happen? What will be your beta 1? Correct. So, first we will find out B1, B2 and B3. See what is your B1 bar? B1 bar letter like this, B1 bar is 70.11. What is your B2 bar? 77.89. What is your B3 bar? 72.67. G same for this case also. So, then we want to find out beta 1, that is the first one. So, 70.11 minus G, that is 73.56. What will be the value here? 73.56, 70.11. So, it will be 5, then 4, then 3. I think this is minus 3.45. What will be beta 2 value? Beta 2 value will be 77.89 minus 73.56. So, you calculate. So, 77.89, 73.56, then 3, I think 4. So, 4.33. Similarly, beta 3 cap will be 72.67 minus 73.56. So, it will be 73.56, 72.67. So, 9, 6 plus 1, 7, 7 plus 8, 15, I think minus 0, this will be this, then ultimately this will be minus 0.89. Again this sum will be beta m, m equal to 1 to capital M, this will be 0. Here our capital M is 3, here capital L is also 3. So, if this is the case, then I think in one of the example I show you that suppose the age effect you want to plot, age effect this side, suppose this is for A1, this is A2 and A3, then what is your A1 value? A1 value is minus 2. So, A1 is, suppose if I go like this, this is minus 2, and A2 is 3.66. So, 1, 2, 3.66 somewhere here, and minus 1.67, 1.67, this will be somewhere here. Similarly, this is all, these are all, this is what is tau L estimate, and these are the, this is A. So, for A1, A2, A3. Similarly, you require to find out also, this type of diagram is better to give for easy understanding. So, what is our beta 1 minus 3.45. So, 1, 2, 3 like this. So, minus 3.45 will be somewhere here, that is beta 1, or here it is for B1, so write B1. Then second one is 4.33, 1, 2, 3, 4, this one for B2. Similarly, other one is minus 0.89. So, we can say this side is beta m and this is B, factor B. Okay. Now, what will be the tau beta Lm? Tau beta Lm, how do you compute? So, how many L equal to 1, 2, 3, m small m equal to 1, 2, 3. So, your combination will be 9 combinations. So, ultimately you will be getting a table like this, where suppose 1, 2, 3, then 1, 2, then 3. So, what is required? What is this? Tau beta cap 1, 1, tau beta cap, this is 1, 2, tau beta cap 1, 3 is coming. Yes. So, similarly here tau beta cap 2, 1, tau beta cap 2, 2, tau beta cap 2, 3, then tau beta cap 3, 1, tau beta cap 3, 2, tau beta cap 3, 3. You require to find out all those values. Okay. Now, once you calculate this, all those that beta and other things, then what is required to know? This is what is the error component. How do you calculate the error part then? Error part is epsilon IL, okay, ILM. What will be this one? XILM, correct. This minus AB bar LM. And in this case, the tau beta LM formula, I think this minus BM cap plus G. This is the formula we have used. No? This is the formula we have used. Okay. So, this formula you will be using. In Montgomery it is given clearly. You go through Montgomery, this one, design and analysis of experiments, design and analysis of experiment DOE. This ABL bar plus minus AL bar minus BM bar plus G bar, that is the formula we have used. So, by this manner now you will be able to compute that errors also. Errors is XIL minus AB bar LM. So, AB bar LM you have already computed, this is the AB bar LM. So, 67.67. Now, what is XIL X111? 68. So, 68 minus this, similarly 65 minus this, 70 minus this. In this manner you will calculate. So, that means the first three observation 68 minus ABL bar is 67.67, then 65 minus 67.67, then 70 minus 67.67. So, this one is I think 0.33. 338, correct. This one will be 65 minus 2.67 and this is 338 2.33. Again you see that sum is 0, this sum is 0. Okay, so in this combination the parameter xi lm bar lm bar all those things. Let me go to the case 0.33 minus 2.67 plus 2.33. Okay. What you will do with these errors? These are all errors, because we have established earlier, I think I am correct, that the your predicted value is AB bar LM and actual value is XILM. So, the error will be the actual value minus predicted value. So, in that sense this is correctly calculated. Okay. So, now what you will do with this error? You have to go for model adequacy test. What are those model adequacy tests? First one is you have to find out the normal probability plot. I have given you the formula how to go about in first class. So, then see it is almost in a straight line. So, we can say this is normal. Second one is you are seeing the independency of the observations. So, in order if you see ultimately residual versus observation order there is no relationship, it is haphazard, random. Third one is do you want to check the covariance, variability across different that groups, this level. So, here also you see you are not finding out much, that the pattern almost it is basically not saying departure from equal variability. So, the adequacy part is also tested. Now, this is our 2-way ANOVA part. So, should I repeat again or it is okay? So, 2-way ANOVA part is you have 4 sources of error variation. One is factor A, factor B, their interaction and error term, random error. These 4 will make up the total sum square. You have to find out the degrees of freedom, test it. Once you test, you reject the hypothesis, then you go for parameter estimation, otherwise no need of estimating the parameters. So, you use the parameter estimation following the rules given to you, except the other only one case that tau beta, this one, and this is the formula. We have computed almost all other parameters here, and you will be able to use this. So, now you will know that what are the values of different parameters. So, are you not interested to find out whether that tau 1 and tau 2 are different or not? Yes. So, first is your that computation of SS, then hypothesis testing, correct. Then followed by what you will do, you will find either you will reject hypothesis H0. Once H0 is rejected, then what you will do, you go for parameter estimation. By parameter estimation, what are the things we want to estimate here? That is grand mean, we want the tau L, so grand mean we want the tau L to estimated, beta m to be estimated, then tau beta Lm to be estimated, and also we want the error to be estimated. Now, in earlier class I have said that suppose there are tau 1, tau minus tau 2. So, you may be interested to compare which of the population or the factor effects are different, and this one is nothing but AL bar minus A1 bar minus A2 bar. Can you remember this? That 2 level mean difference. What test you will use for confidence interval? Yes. So, expected value is what you are looking for, that your mu, I think I can say, if I say A1 minus mu A2, A for the factor and two different levels. Then what you require, you also require to know that what will be the, that A1 bar minus A2 bar, that is the sample value, minus then A1 bar minus A2 bar, then plus some values, where from you got these values. Okay. So, you can go for Bonferroni method, okay. You can go for morning, I say the Taki method. If you use Bonferroni method, ultimately you will be using T distribution and number of comparisons are there, that to be the alpha value has to be adjusted or weighted using the number of comparisons. If you go for Taki method, you will be using the studentized range statistics, studentized range statistics. Okay. That is basically Q alpha number, that where for what, this is for factor A. So, number, that is the number of labels in factor A, then what is the error degrees of freedom, okay. This into MAC by N. So, here this one will come, this will come here, this will come here. Okay. We can see that what we have written earlier in one factor case, you see that Q alpha AL MAC by N. Okay. So, we will follow this formulation. Similarly, you will go for beta m, you can go for tau beta LM and all those things. Then once these things are completed, you will be able to find out which are the factor labels are different for factor A point of view, for factor B point of view, and you will be more interested to know this one, the interaction effect. How do you know the interaction effect? Basically, if I go back, for example, what do you want to know? We want to know like this. Suppose this side is my B factor, this side is my A factor. So, how many levels are there for A? 3 levels, A1, A2 and A3. Now, B also having 3 levels. So, I will take the B1 first, correct. So, if I take B1 first, if I go to this figure, you see, if I will not consider these two, I will consider only B1 fix, then A1 value, A2 value, A3 value, these are the AB LM bar. So, instead of this, you will be plotting ultimately tau beta LM. So, this will be this plus this minus this minus this, and then that value will be, you will be getting. So, you may get some value and ultimately you may get like this. So, this is for B1. You may get a situation like this. This is with respect to B2. When you get this type of cross section, intersection is there, then you will say that interaction is significant. There is interaction. So, in general, if I find like this, suppose two factors are going like this, suppose this is my A and this is my B. So, let it be B1 and B2. If two factors plots are going like this is parallel, no interaction. And when there is interaction, you will be getting some cross, means this line will not be parallel. So, this shows interaction. Now, whether the interaction effect is significant or not, you have to use the statistical formula using your Bonferroni, using your even Taki test also will give you, or simple the first level formula we will use. Okay. In Taki test we will test the we will test the hypothesis the difference is significant or not. Okay. So, that means ultimately where we are standing now, you know the interactions are also known, and then after that your work is that model adequacy testing. So, under model adequacy testing you will be doing normality test, then independent observation test, then your equal variance test. Okay. Now, you will be doing all those tests from error data, error and fitted values wherever required. And please also remember that it is always advisable that when you get a data set, better remove outlier. Remove outliers before fitting to models, you remove outliers, then you also test their normality of the data, normality you test. Also you can test you go for Bartlett test for equal variance. So, these are the first thing you will do, then you fit the model, then you go for hypothesis testing, parameter estimation, interaction plots, error, all those things, computation, then finally again you recheck with the error data that yes, the assumptions are satisfied. Okay. So, this is what is two-way ANOVA. Now, we will go for another example explaining the three-way ANOVA case. Okay. Here read the problem. In order to evaluate the safety performance of employees in a coal mine, this study it is a real case. We have done it, but here I am showing you the partial results, because I have not taken all the variables, only a few variables I have taken here. Literature suggests that occupation, age and experience of workers play a significant role. In an exploratory study, we investigated the influence of these three factors on safety performance measured on a 100-point scale. The variables with categories are given below. What we have occupation, there are in mind that loader is a very dangerous group, prone to accident because of the many reasons, particularly the hazardous working condition point of view. And non-loader mean other than loader, they all are non-loader. Then age we have categorized into two groups. We are saying that less than equal to mean age is group 1 and greater than mean age is group 2. This is abrupt breaking of the age, it can be better broken. For example, young, middle, old like this, but here to demonstrate the applicability of three-way ANOVA, we have reduced this one. Similarly, experience also we have categorized into two groups, less than mean years of experience and greater than mean year of experience. And this is a standard process also. Many times we categorize continuous variable or dichotomize basically continuous variable under less than mean, greater than mean conditions, less than equal to mean, greater than equal to mean. Then the response variable here is safety performance, which was given by a safety supervisor, basically who observed the people, that he over the years he has rated that okay, this is his performance under 100-point scale. Then question, the research questions here, Do the workers across job titles differ in their safety behavior? Do the workers in different age groups differ in their safety behavior? Do the workers in different experience group differ in their safety behavior? Are there interactions among job title, age or experience groups? Very vital, very significant questions these are, because if we find out that there is difference across job titles, so the prevention action will be accordingly taken. If there is no difference across the job titles, it may so happen that the working conditions are not affecting. It may be something else is affecting, or all the working conditions are equally hazardous, because the safety performance in the mine studied are not good in that sense. Okay, so you can answer all those questions. So, if in order to answer this question, if I ask you what are the sources of variation, we have to use ANOVA. So, definitely you will say first is job title, what will happen now? Okay. So, job title factor A, then second one is our age group. So, age groups, that is your factor B. Third one is experience group, this is your factor C. So, we have 3 factors each with 2 groups. We are saying it 3-way ANOVA because 3 factors are considered. So, if I say that what are the sources of variation, then you can write here the sources is first is factor A, then factor B, then factor C, interaction AB, interaction AC, interaction BC and error. Is it problematic? Very simple. So, this is the beauty of ANOVA. ANOVA is not conceptually that difficult, it is easy to understand also. So, SS you will be calculating SSA, SSB, SSC, SSAB, SSAC, SSBC and SSE. Then definitely the last one is SS, that is the total one. So, your degrees of freedom you write down, then you write down that MS, you write down F. Getting me? We have taken 2 groups at each of the variables having 2 levels. So, 2 minus 1 1, again 2 minus 1 1, 2 minus 1 1, 1 into 1 1, 1 into 1 1, BC 1. There is one more sources of variation, that is what? ABC, 3-way interaction. So, that also will become 1, and what is the number of, it all depends on the number of observations you will be taking, that n minus whatever degrees of freedom 1, 2, 3, 4, 5, 6, 7. So, 7, that will be n minus 7, n minus 1 will be the total. So, n minus total minus 7, the n minus 8, n minus 8 will be the error degrees of freedom. So, you will be finding out MS accordingly, then for every factor you will be finding out the F value, and you have to see that whether there is difference or not. Okay. Let us see that the study. Now, we have take these are the basically the group and there are 300 observations. So, total observation is 300. Okay. Now, see the observations that job title wise, this is basically the category wise and X wise we have given. Suppose what I mean to say, loader less than 37.3 years of age and experience less than 14.58, these are the mean age and mean experience value 93. So, the distribution is very skewed. You see only 2 observation available 2 in this combination. Loader less than 37.34 years of age and greater than 14.5 years of experience. This is quite obvious, but this low value definitely distort the total authenticity of the estimation. Okay. Now, this is one concern. Another concern is this is 5, only 5, but 5 and more we consider acceptable. So, only this portion is difficulty, but other cases there are reasonably good amount of observations available. Okay. In reality, this is a big problem. When you go for real study, then you will find out this type of problem. So, what will be the alternative to avoid this problem? Your study design must be good enough. What do you mean by study design? Before collecting data, if you know that okay, this is my structure. Now, you have to know in your system for in this particular combination how many people are working. All combination, what is the present level of people or number of people working, getting me. So, then you randomize based on this. What I mean to say, suppose my first combination there are n1 people working, or I can say that capital N1 people working, second condition n2 working, third condition like this n3 working. So, then you will sample n1 from first, n2 from second, n3 from third in such a manner that there will be frequency matching. But in no case, so one issue is frequency matching. So, if I know that in reality there is not, only very few people are working in this group, so this is not a good group. But anyhow, what we have happened, we have first collected the data and later on we have seen, and that is why this problem is occurred. This problem will occur to you also if you do not do the study design correctly, what I have discussed in first class study design. Anyhow, with this data we have done the ANOVA analysis. This is 3-way ANOVA. You see SSA, SSB, SSC, SSAB, SSSC, SSBC, SSABC, SSE and SST. So, these many sources of variations, and these are the sum square 519.07 coming from factor A, that is the occupation or job title in this case. Then 120.51 is contributed by age, 585.10 is contributed by experience. The job title versus age interaction contributing very less 10.27, but job title vis-a-vis your experience there is large amount contribution is there. Then your age versus experience interactions, the value is 274.76, but the 3 factor interaction case the sum square is very less 2.93, and there is a large amount of, what is this, the error one, very large, and SST will be ultimately the sum total of all those will be the SST. And as I told you, there are 300 workers. So, 300 minus 1, this is the degrees of freedom for this, and everywhere we are getting 1 degree of freedom for all the other sources. So, error term is 292 that degrees of freedom, and in the usual manner you have computed MS and you have computed F. Interestingly, you find out that none of the factors are significant. Getting me? So far what I have shown you? I have shown you that yes, there are some factors significant, some interaction effects also significant, but here what happened, we found out that hypothesis testing is saying that none of the factors contributing. Then what we will do? Ends, your work ends here. What is the point in carrying forward? It is not required. So, why this has happened? because there may be 2-3 reasons. One of the reasons could be that the variables you have chosen, they are not contributing. Second one, I showed you that the study design might have been wrong. So, concept literature says there must be difference. For example, particularly the young versus old workers, the less experienced versus the more experienced workers, this literature says, but literature is not says that the less than equal to mean and greater than equal to mean year of experience or mean years of age, that may not be distinguishing this one. So, if we go for different categorization, it will give you, it may give you better result. So, ANOVA as a technique, fine, this is one way you are doing, but when you come to this type of situation, please remember, I am now stressing it because we are now entering into the modeling part. ANOVA, MANOVA, these are all models, then multiple regression will be another model. Okay. So, that is why what is our conclusion? There are no differences, this is for the 3-way ANOVA part, in safety performance across job title, age, and the researcher needs to redesign the study with other relevant variables. Okay. So, I hope that now for 3-way or for more way ANOVA, this is unbalanced case. What is the balanced and unbalanced case? Balanced means the equal sample size, unbalanced means across different groups there are different sample size. Okay. So, our factor A, so when you are making them different groups, sample size are different. Similarly, factor B, that may be different. Similarly, your factor C, that may be different. When they are equal, that is known as balanced ANOVA. When they are different, that is known as unbalanced. And unbalanced ANOVA is problematic, because you will find out one of the issue will be that equality of error, your population variance, level variances. It is most of the time from real data you will find out that there is difference. Any question related to this? So, thank you very much, and next class I will show you one case study on MANOVA. So far ANOVA, I think we have done enough discussion, and MANOVA case study is the next class topic, MANOVA case study. Okay, thank you.